high probability. Once in a while may be a high PT interaction, not always. That is, the probability of high PT interaction in this case is small, and probability of having low PT or soft phenomena is large. Now whatever happens here can be lumped into the X. That is, PP is scattering, producing some hard scattering, not E here anymore, producing some hard scattering plus some X which are not observed. These are called spectator quarks. Same with this. So for a while then our picture of proton-proton scattering is PP going to, cross section of PP going to some final state is actually integration over the x variable of the Bjorken x, then fx1, fx2, and then sigma going to photon to the final state. That is, the final state which we wish to observe is produced by the photons. But since we do not know which photon participated, remember quarks are unobservable. Therefore, we assume that they have been produced with two photons carrying x fraction of the proton momentum. So this guy carries x1 fraction of the proton momentum, this photon, and this guy carries x2 fraction of the proton momentum, and these two scatter to produce the final state. But of course, they do not carry a definite fraction of the proton momentum. They can carry all possible proton momentum fraction from 0 to 1. Therefore, the probability. So if somehow we know from other experiments, deep inelastic scattering or neutrino scattering, many other possibilities, then we know F's. If we can calculate the point-like particle scattering, which we should be able to do because these are scattering of two point-like particles, these are computable. From first principles. We are home. We calculate PP scattering. So from theory, which is quantum field theory, and from experiment, which is the determination of the photon density function, we get the ingredients for doing this calculation, and then you do this calculation. The calculation of course has to be done numerically because the photon density functions are complicated, but at least the structure of the calculation is clear. Now I will show you one or two examples of this kind of calculations, how we actually do it. One will be very simple, the other will be more complicated. Let us wait for that, but before we jump into that, let us make some very rough estimates. Now, in the very first lecture, when two particles are colliding, I discussed the importance of the center of mass energy. You remember why? Suppose we are producing new particles, A and B scattering to produce C and D. Now, what is the importance of the center of mass energy with respect to particle creation? You remember? What determines whether that interaction will be able to create the particles or not? It is the center of mass energy. The physics is very simple. In the center of mass there is no total momentum of the initial particles. Therefore, the final state particles can be produced at rest without violating momentum conservation. Therefore, the entire center of mass energy of the initial particles can be converted into the mass of the final state particles. So, this formula you should remember for understanding the discussion during the next center of mass energy, which is normally denoted by square root of S. This is the common notation. This has to be greater than or equal to mc plus that is, if A plus B produces, maybe I denote that this is the center of mass energy of AB and the scattering is A plus B going to C plus. However, in this case, it is the partons which are colliding, right? Not the protons. Therefore, first we have to find the parton center of mass energy in terms of the proton center of mass energy. This is the first task. And this calculation is fairly straightforward. So this is like that. So let me write a quantity called S hat. Whenever I have a hat, it means that it is a parton center of mass quantity. So this is must be equal to the this is how we introduce the center of mass variable, and then P1 square and P2 square are 0 if we neglect the parton mass in this high energy process. Then this will simply be the dot product of P1 dot P2, and since P1 is x1 capital P, this is x2 capital P. Therefore, it turns out to be, maybe you can write nearly equal to because you have neglected the squares. You do a little exercise in computing this 4-vector dot product, and you will find that this is equal to 4 times where E is the proton now this 4E square is actually the S variable for the 2 protons. Oh, I am sorry, I dropped X. So this is simply x1, x2 square root of capital S, which is the proton center of mass. Now suppose you are producing a single particle via this hard scattering, like the production of a W boson or a Z boson. In that case, so these two objects scattered to produce a single particle in the final state. Then you have root S hat x1 x1 x2 square root of s or only s, because there is a square here. Sorry about it. E square is s is square of p1 plus p2. So I have e square there. So this should be equal to s hat. But for a single particle production, S hat then must be greater than or equal to m, where m is the mass of the single particle. Inequality is that the particle may also be produced with kinetic energy. But the minimum value of S hat is equal to the mass of the particle.
So it should be m or m square.
Yes, dimensionally it should be m square. Very good. Thank you. Therefore, we find a fantastic result. Simple, almost high school physics, but very, very informative, and that is now what does it tell me? It tells me that the W boson was created for the first time in the 1980s at the CERN Piberpi collider. The machine had a rootase of 630. For simplicity, let us make it 640. So, W production at CERN in the 1980s, actually the year was 1983 probably, or maybe 82. What is the mass of the W? 80. What is the S value? So what will be the thing like? Well, it is about 1 upon 8, right? 1 upon 8 you can approximately write it as 0.1, and then this will be 0. Which means that the product x1 x2 has to be 0.01. So do you expect valence quark to interact in this case, or the C quarks? Remember, C quarks are important at x1 x2 10 to the 2 or something, right?
X is small than c quark.
No, x is 0.1. It is not 10 to the minus 2. So in this process, definitely a valence quark from this was a proton antiproton collision actually. So a valence U from the proton and a valence D bar from the antiproton. They were contributing and producing a W boson. But suppose this is LH. You want to produce this in the LH. Now what is the value? You remember? Now it is the total center of mass energy is 13 tera electron volt. That means W is in GeV. So this is 13 times 10 to the minus 3 already, and this is then 80 by 13 is to 10 to the which means that the colliding quarks are very likely to be coming from the C, and it has to be, because it is a proton-proton collision. Proton do not have an antiquark. So at best, one proton contributes one valence quark, but the other proton has to contribute a q bar, which is a C particle. Proton has no q bar, antiproton hat, because it is the charge conjugate of the proton. So therefore, this is a process which gets heavy contribution from the C quark. So let me go to the pictures. So this is the picture that a quark and an antiquark scatters to produce the W, which then decays into positron and neutrino. What happens if I consider not a single particle production but a pair production of, let us say, two top quarks, m top and m top. What happens then? This equation remains unaltered except for the fact that this root S hat now must be more than 2m top square. What is typical x1, x2 again? It has to be greater than or equal to 2m top by S. Again, for simplicity, take the topmost to be 200. It is 170, but for a quick estimate, let us take it 200. So we have 400 in the numerator divided by, oh, I am sorry, it should be root S. So if you put for root S the CERN value, which is something like 600, then you will get something like 2/3 whole square, which is something like 4 by 9. Now that is a very large number, and the probability for the valence quarks even, they are typically 10 to the minus 1, maybe a few times 10 to the minus 1, but having a value something like 2/3, their product has a value something like 4/9. That is practically impossible, and no wonder we did not discover TT bar at the CERN collider in the 80s. What about LHC? Uh, 13 TeV, let us make it 10. Now what you get out of it? You get 40 by 1000 whole square, and clearly this is something like 4 times 10 to the minus 4. So now you see the product of x1, x2 is going to be of the order of 10 to the minus 4. So this is the region where gluons and C quarks are contributing. This is the reason why LHC is popularly known as a gluon machine, because of the large center of mass energy Most of the time the